My name's Adam. I'm one of the first-year fellows in infectious diseases. And I've chosen the topic today, some important historical discoveries in the infectious disease world. Why did I choose that? One, I think it gives us a really good context for what we're doing. It shows us where we've been, where we're going. Kind of brings back some of that excitement to our work that some of us may have lost. Also, in undergrad, I did an archaeology degree, so I love history personally. So personally, I find it very interesting, and I hope to impart some of that interest to you all today. So I have a few goals just quickly for this presentation. I'm not going to do an exhaustive study of every single important historical discovery in infectious disease because that would take 2 weeks. So what I will tend to focus, actually what I am going to focus on, is what's been termed a golden age of bacteriology and microbiologic discovery. When was the golden age? That was basically in Europe in the 1880s. So most of the people I will talk about were people in Europe, 1700s and 1800s, and really focusing it towards the end on the late 1800s. So here's some good quotes on history. MLK said, "We are not makers of history, we are made by history." Harry S. Truman said, "There is nothing new in the world except the history you do not know." And Philip Gadala said, "History repeats itself, historians repeat each other." So that's probably at some level what I'm going to be doing today is repeating other historians. And with that in mind, a very important historian who I really enjoy is Paul de Crieff. And he wrote a seminal work back in 1920, I think it was 26. So penicillin had not been yet discovered when Paul de Crieff wrote his book, Microbe Hunters. And he was talking about the important discoveries up until that time. So some of the stories are gleaned from his work, but really you have to fact check a lot of what he says. He's long since deceased, but he was quite an embellisher. I don't know if this book could fit into the terms of historical nonfiction, just because he embellished his own account, but it's close. So a lot of interesting stories. So to begin with, I want to briefly mention the Miasma Theory. In antiquity, how people thought other people contracted disease was from this substance called miasma, which means pollution. And this phrase was coined by Hippocrates. We've all heard of him. And really this pollution was a result of the bad air that people would breathe in. So things like the plague, Black Death, cholera epidemics, pandemics would be due to pollution, bad air. And bad air in Italian, malaria, malaria. That's where we got the term malaria. People thought in the Forum in Rome, when they came down with malaria, it was due to the bad air. And what Hippocrates says and the prevailing opinion was that this pollution rose from decaying matter. So as things died and decayed, there was a bad smell. It was full of whatever caused infections, and the bad smell is bad news. And around that time, there was some thought that people could pass these infections to others. Thucydides mentioned this in a plague in Athens in the 400s BC. But really, the thought that it was transmitted by miasma was the prevailing thought. So that brings us to Antonie van Leeuwenhoek. It's kind of where the journey begins. And he was from Holland. He was a business owner in the late 1600s, early 1700s. He's known as the father of microbiology. He was the son of a brewer and owned a dry goods store, and he sold drapes. And it's not quite clear why he started grinding his own lenses. Many people think that he was trying to inspect the quality of the drapes that he was producing. But at any rate, he was grinding these very, very, very tiny lenses, and he started looking at everything, not just the drapes, but small specks of dust, small plants, any sort of thing, a drop of water from the creek. And really, these microscopes that he invented are remarkable for the time. Some are believed to have been up to 500 times magnification. The ones that survive are at least 275. So he was a member of the Royal Society in London, a very important historical scientific society in Great Britain. And he corresponded regularly with the society, and he wrote his many detailed observations of what he was seeing. in his microscopes. And some of these discoveries are bacteria, protozoa, spermatozoa, among many others. So without Leeuwenhoek, we wouldn't really know about microbes. Here we see one of his early microscopes there on the left. The lens is the very small little circular dot here. He would have a little pin on which to affix the sample, and then by rotating the device any number of ways, he could do focus. And obviously where we are today. So I'm going to try to tie, sometimes with humor, sometimes without, some of these people as to where we are with what they've helped us accomplish. So that brings us next on to Spallanzani. He's maybe one not many people have heard of. He was an Italian priest in the mid-1700s. He was the chair of natural history at the University of Pavia in Italy. And he actually started work on disproving the theory of spontaneous generation of microbes. Up until that time, people thought that microbes appeared out of nowhere, that they begat themselves. And every inorganic substance and some organic substances had a vegetative force through which they regenerated automatically. And Paul de Kreef says it this way. He says, "The great majority of sensible people believed that many animals did not have to have parents, that they might be the unhappy, illegitimate children of a disgusting variety of dirty messes." So there were many such theories about how how diseases came into being, or any sort of number of things. And here's a recipe. So Jan Baptist van Helmont, who was a Flemish physician in the 1600s, one of his spontaneous recipes for spontaneous generation was: you take some dirty clothes, you add some wheat, you mix in a little thyme, and all of a sudden you've got rats. It's like, oh wow, where'd the rats come from? Obviously they spontaneously generated. There are many examples of these fun recipes. So there was actually another smart Italian in the mid-1600s, Francesco Redi. He made the following observation. Well, he had an unsealed flask and put some meat into it. And as the meat rotted, voila, there were maggots. And people said, well, of course, maggots arise from rotted meat spontaneously. However, he put a piece of rotting meat in a sealed flask and did not notice the spontaneous generation of maggots, which was, completely simple but completely brilliant. And then he did the same experiment with a piece of gauze on top, and whereas the bad smell, the pollution, the odor arose out of the flask, on the meat itself there were no maggots. So Spallanzani himself kind of perfected this a little bit. It wasn't completely perfected until Louis Pasteur, but so what he did is he heated some broth, a mixture in which bacteria were known to grow. In one instance he left it open to the air, in the other instance he corked it. In the one that was sealed, nothing grew. In the one that was open, there was bacterial growth, and thus laying the groundwork for saying, yeah, this isn't right, your idea of spontaneous generation. I'm trying to go in a chronological order to kind of give you some sense of some contemporaneous microbe discoverers at the same time. So a little later was Edward Jenner, and we've all heard of him. He was the father of immunology. So he built on a concept of what's called variolation, not vaccination. It's a little different. So variolation was a practice actually used by even the ancient Chinese. And what they would do is they would take scabs from people infected with smallpox, and they would grind it up, and either they would sniff it and inhale it, or they would do superficial scratches on the skin and put these scabs there. And they noticed that sometimes it would work. It would impart some sort of immunity to the recipient. So, and he also made another observation that milkmaids were generally immune from smallpox, variola. And so he postulated that the cowpox virus, which is related, and he postulated that relationship. So what he did was, there was an 8-year-old boy, James Phipps, I think it was the son of one of his gardeners. He inoculated this young boy who was 8 years old with cowpox. And then the young boy came down with a mild viral syndrome, and then he was also subsequently, experimenting on humans, okay. He was inoculated with smallpox, and he had no reaction whatsoever to smallpox. I don't know how he got the guts to do that. So vaccination is from the Latin word vaccinus, which means pertaining to a cow, cowpox. That's where we come up with the word vaccine. And Really, as we all know, variolation fell out of favor, and vaccination fell into favor, as vaccination was far more safer and far more effective than variolation. And so without Edward Jenner, we wouldn't have vaccinations. I know that's a simplistic way of thinking about it. And without vaccinations, we wouldn't have Andrew Wakefield, everyone's favorite, the British physician who wrote a paper in 1998 saying that vaccinations cause autism. So I don't know if y'all have read about the recent, I think it's a measles outbreak among the Somali community up in Minneapolis, Minnesota. And he's directly tied to that. That's very sad. Next on the list is Ignaz Semmelweis. Many of you may have heard of Semmelweis. He was Hungarian, about the mid-1800s. He was a doctor on obstetrics wards, and he had teaching wards, and there were midwives' wards. And he was noting, wait a minute, we've got this puerperal fever, which is postpartum infection. Puerperal fever was way too common on the teaching wards. In fact, the midwives' wards, the mortality of puerperal fever was 3 times less. And he noticed this between 1841 and 1846. On the teaching wards, mortality was 10%. On the midwives, it was only 3%. And in fact, people were begging not to be admitted to the teaching service, and they were instead giving birth in the street instead of being admitted to the physician's side. They were demanding to be admitted to the midwives' clinic. So he said, well, what's the difference? What's going on differently? Some people have thought that it was, the midwives washed their hands. There's no way to prove that. But what Semmelweis observed was that the physicians would come back from the anatomy lab. The midwives were not allowed into the anatomy lab, but they would come back from the anatomy lab, and they were bringing some sort of material with them from the anatomy lab into the wards. So he was like, well, if we're bringing this bad material into the wards, how can we get rid of it? He noticed that there's a substance, bleaching powder. It's calcium hypochlorite. We actually use it today. He thought, well, if this substance can remove the foul odor, the miasma from these cadavers, could that be used to disinfect not only hands, but surgical tools as well? So he started using and becoming much more common under his watch the use of washing hands with these solutions. However, he was unfortunately completely ridiculed by the scientific community of his day. He actually ended up suffering a complete nervous and psychiatric breakdown. He had a psychotic episode and was committed to an insane asylum, where he died of septicemia later. So I just kind of threw in, just for our memory, what are the common causes of postpartum infection? Well, it's not miasma. Postpartum day 2 to 3, we're going to get this polymicrobial mixture, aerobes, anaerobes, group B strep, gram-negative rods, Bacteroides, Clostridium. So really, without Semmelweis, we would not have contact precautions. So also calcium hypochlorite, we use it really we use it in public swimming pools to sanitize them, and really also to disinfect drinking water. And that brings us to Louis Pasteur, really a giant of his age, a French microbiologist and chemist who in his own lifetime was praised. He dabbled in many sciences. He proved that yeast was the agent responsible for fermentation for alcohol from sugar. And from this, he proved that beverages were spoiled to growth of microbes. So by then, everyone, understood about microbes, but they didn't know what effects that they had at the time when he was young. And so he's like, well, if these microbes that I'm finding in these, growing in an abundance in these spoiled beverages, what can I do about it? And so he found that when he heated the liquid to a certain temperature, many of these bacteria and organisms would die, but not completely. You had to have organisms for fermentation, but if you killed all of them, you would have fermentation. If you killed most of them, there came into a practice what was called pasteurization to keep the liquid from spoiling. So Pasteur and actually others of his time thought, well, if microorganisms cause the souring of beverages, are they responsible for not just diseases in liquids, but diseases in humans? So he found a very interesting observation. He was working on chickens and cholera and finding out, here's chickens and here's this cholera, and it looks like this organism that I'm isolating is causing this disease. And he actually, this is a very interesting observation, there was an improperly stored, they were trying to prove that the organism caused cholera. And they were keeping colonies of the cholera, and one of them was improperly stored and spoiled, and he saw that, oh, wait a minute, this doesn't really cause cholera in this chicken, so maybe, well, either one, this organism doesn't cause cholera, and we're wrong all along, or two, it's a weakened strain, and it causes a milder case of the disease. So what he did was start to use that concept of weakened organisms to protect against disease. This was different than Jenner. What Jenner was doing was using a related organism, in that case, cowpox, to confer a cross immunity on somebody. This was a weakened version of that organism to induce a immunologic response, although they didn't quite know the ramifications of that at the time. And it was also Pasteur who started to use the term vaccination universally for everything, instead of just cowpox for smallpox. And he actually ended up applying this method for anthrax, and he ended up immunizing goats and cattle against anthrax. So, and then, like I said earlier, it was Louis Pasteur who settled once and for all the debate of spontaneous generation. The only thing that he changed about Spallanzani's experiment, he added a gooseneck to the top of the flask so that it didn't have to be sealed, and that the organisms were trapped on the inside of the neck of the flask on the way in. And so if he tipped it over, there would be growth. But if he just let it standing upright, nothing would grow. And that, once and for all, killed the idea of spontaneous generation. So Pasteur worked with many scientists of his time, and one of them was Émile Roux. And Louis Pasteur actually also produced the first rabies vaccine. So at the time, the cause of rabies was not known. And it was really, the reason why it wasn't really known is because they couldn't cultivate it. You can't just grow it routinely using their methods at the time. So what did they do? They infected rabbits with rabies and then grew the rabies virus in the spinal tissue of the rabbits. And then after that, they left the infected tissue to dry for a long time. And then it was anywhere between, I believe it was 2 to 14 days. And then they would use the dried nervous tissue from these rabbits, and they would inoculate into dogs and other rabbits this dried tissue. They would give a series of inoculations over 2 weeks. And then, after that, they would directly into the CNS tissue inoculate the dog or rabbit with known active rabies CNS tissue. And they demonstrated a protective effect of this vaccine. So after Pasteur had successfully demonstrated this, he actually performed the first successful vaccination on a human. And it was a young boy named Joseph Meister who ended up living. He was bitten by a rabid dog, and it was very soon after Pasteur found this vaccine, and his mother had heard, and obviously, as any mother would do, came crying to Louis Pasteur and said, "Please save my son." And the controversy was that Pasteur was not a physician, and he did not have license to treat humans. But he conferred with some physician colleagues that he had, decided to do the inoculation, and the boy lived. And as you can imagine, all over Europe, people started clamoring for Pasteur to come and save their loved ones. And actually, Joseph Meister ended up becoming the caretaker of the Pasteur Institute in Paris until he was 40, when the Germans occupied Paris, and he actually ended up killing himself. So without Pasteur, we wouldn't have really everything. We wouldn't have pasteurization, vaccinations, really anthrax, rabies, cholera. We wouldn't have once and for all disproved that rabies and zombies aren't actually linked. So Joseph Lister, he was a British surgeon, mid to late 1800s, the father of modern surgery. He used Pasteur's work, and he noticed, well, based on what Pasteur was doing, there's a few ways to get rid of these microbes. Either you filter it, you expose it to heat, or you expose it to chemicals. And he was doing surgery on humans, and he couldn't really do any of the first two, so he had to resort to using chemicals to kill these microbes. So he really pioneered antiseptic technique, and he used phenol, carbolic acid, to sterilize equipment. And the surgeons who worked under him had to wear gloves, clean gloves, and wash their hands and surgical equipment before and after with this solution. And so without Lister, we get a lot more consult for surgical site infections. Robert Koch was a very interesting German physician and microbiologist, a very, very strict scientist. He's known as the father of modern bacteriology, and he actually had an ongoing interesting rivalry with Pasteur about scientific method, reporting of results, whereas Pasteur was very imprecise and bombastic. Koch was meticulous and scrupulous. He actually positively identified tuberculosis, cholera, anthrax, and actually anthrax was the first organism, and it was Robert Koch, to have a definitive link between the German disease. How I was saying with Pasteur, he was trying this cholera on the chickens but couldn't really prove it. It was around the same time that Koch proved anthrax caused the disease of anthrax. He's also pioneering in various stains. And he was one of the first to isolate pure colonies on agar. One of his assistants was named Petri, you may have heard of him. This really led, his experiments, Robert Koch, led to his famous 4 postulates. Many of you may have heard of Koch's postulates before. And these postulates were very important, still are these days, although they no longer apply to everything. But these postulates establish criteria for a causative relationship between germ and disease. So the first thing that had to satisfy his criterion number 1, you have to find the germ, the microbe, in every case of the disease. You have to be able to isolate it. Not only do you have to find it in disease, you have to grow it in culture, every instance. Once you grow it in culture, you inoculate it into a disease-free animal. The animal must come down with that disease. And number 4, once that animal comes down with that disease, you have to grow the same bug out in culture again. And then obviously in healthy subjects, it wouldn't apply because they didn't have the microbe in them. Today, this doesn't apply to all infectious diseases. I mean, many viruses, oncoviruses, asymptomatic carriers, prion diseases, many other things don't follow these rules. His rules have been updated, but this was one of the very first early attempts at this sort of scientific reasoning behind germ and disease. Very elegant. Robert Koch was actually the recipient of the 5th Nobel Prize for medicine or physiology, and it was rewarded to him for his investigations and discoveries in relationship to tuberculosis. If you remember, I said that he was the first person to positively identify the cause and relationship in tuberculosis. One of Pasteur's students, Emil Roux, and then a colleague over in Germany, von Behring, really they were seminal in cholera antitoxin. So this was a few years later, late 1800s. They worked with a physician named Loeffler, you may have heard of him, and he had discovered that Vibrio cholerae, which had now been established with Pasteur, it was not established, but with them it was established to cause cholera. But they could only find it really in small amounts in the throats of deceased children or adults. They expected to find it swarming throughout the body in the millions. And so they postulated, well, maybe it's not the bacteria, maybe the bacteria produce something that causes disease. And they theorized, well, maybe it's a toxin. So what Roux was able to do, from diseased animals, he pulled out a serum, and he highly filtered this serum, had no bacteria in it whatsoever. And he proved that this serum, without bacteria present in this liquid, he was able to inject it into guinea pigs and killed them. So he proved, yes, there's a toxin that causes cholera. So what Behring did is he isolated serum from guinea pigs that had cleared the disease completely. And he found that this was protective against people that had contracted the disease, and he coined the term antitoxin. Very first time that something like this was even heard of or thought of. So Behring, the gentleman on the right, the German physiologist, he actually won the very first prize, Nobel Prize in medicine, and this is 1901. It's easy to count because it starts in 1901, number 1. And so he won it for his work on serum therapy, especially its application against diphtheria, by which he has opened a new road in the domain of medical science and thereby placed in the hands of the physician a victorious weapon against illness and deaths. So really, the antitoxin wasn't 100%. But throughout recorded history, cholera is one of the most devastating epidemics that would recur with some regularity. There was a pandemic in Europe in the late 1800s, 1881 to 1891. France and Germany would kill about mortality rate 50 to 60% among children. And then there was another pandemic closely followed in the early 1900s, began in India, killed about more than 800,000 people, and then spread westward. And really, once this antitoxin, this serum, was introduced, Roux and Behring were hailed as, just like Pasteur, saviors of mankind, especially of children. So we come now to our first American in this presentation. His name was Theobald Smith. He was an epidemiologist, 1859 to 1934. And what he worked on was Texas cattle fever. And what was being noticed was there was this infection among cattle that decimated herds, and it only occurred during the summer. And what was interesting about it was there were cattle in the north and there were cattle in the south in Texas, in the northern America. So the northern cattle, who would be brought down to Texas, trade, being sold, they would die in a month. It was the summer, and they would die within a month. Okay, interesting. The southern cattle stayed healthy. However, and then when you had the southern cattle being shipped to the north, they would mingle, and then within a month, again, the northern cattle would die. The southern cattle would be disease-free. And then Theobald Smith made an observation. He's like, well, there sure are a lot of ticks around on these cattle. So he went with it and composed an experiment. So he had several fields, including cattle from the northern and the southern states, as well as thousands of ticks. So he had a few fields. He had one field with the southern cattle and ticks, and the northern cattle. Northern cattle all died. Another field, southern cattle, no ticks, and northern cattle. Northern cattle were great. They lived. They didn't die. And then finally, field with only cattle, southern and northern. Last field was no southern cattle, but ticks, and the northern cattle, the cattle all died. So he found that it was this tick, which is now named Babesia by Gemina, and Babesia bovis. This tick, Rhipicephalus microplus, would transmit this disease, and he saw it in the red blood cells of infected organisms. And the interesting thing is, well, when's the life cycle? It's during the summer. How long does the life cycle take? About a month. For the entire life cycle of the tick latching onto the cow, actually goes through several molts on the cow itself, falls to the ground, lays eggs, and repeats. And it took about a month. And that was the causal relationship. And this is important because this is the first time an insect vector of disease had been proved at all. So we would be clueless without him. Here's an interesting quick side note, and we're getting kind of into the insect vector diseases. We have Ronald Ross and Giovanni Grassi. They were both physicians, contemporaries, and they both worked on malaria, and they got in a huge fight. Ross proved that mosquitoes transmitted malaria, but only in birds. But he was the one who proved that mosquitoes transmitted malaria. But Grassi, he described the complete life cycle of Plasmodium falciparum, and he showed that only the Anopheles female mosquitoes spread it, whereas Ross had no clue. He just called it a mosquito. He didn't even know there were different types of mosquitoes. And this was a huge stir because Ross was actually the one who won the Nobel Prize. By all rights today, they would have shared it. And it was this big scientific stink at the time. But Ross won it. It says, for his work on malaria, by which he has shown how it enters the organism and thereby has laid the foundation for successful research and methods of combating it. So thankfully today there's a lot more sharing of Nobel Prizes. And that brings us to Walter Reed. Walter Reed was an American U.S. Army physician. He was a major in the Army, 1851 to 1902. He was assigned to Cuba during the Spanish-American War. That's 1898. And at the time he was there, he proved there was a typhoid outbreak due to food and water contaminated with fecal matter. I mean, that had already been proven. But that kind of established his expertise in Cuba. So after the war, he went back in 1900. And he was on appointment there from the Surgeon General to figure out what's going on with yellow fever. We've got all these cases of yellow fever. We don't know what's going on. At the time, yellow fever was thought to be transmitted by dirty clothing, what we would call today fomites, basically the soiled clothing of humans who were killed by yellow fever. However, here's the rub. In order to study yellow fever, they didn't have any test animals. They couldn't get yellow fever in anything, although today we know that it does affect some primates. So unfortunately, he needed human test subjects, and that was pretty much unheard of, except for, all the times that Louis Pasteur did it. So what he did was, with the U.S. government's blessing, he offered some of the men under his command about $300, which is about $10,000 today, to participate in an experiment that could cause them to contract yellow fever. However, everyone refused the money. No one would take it. And it was an honor issue, if you would even believe it today. People pass up on money. Not today. And especially at the time, the mortality rate of yellow fever, 50 to 85%. No lower than 20%. So they had at least a 1 in 5 chance if they caught it to die. And they volunteered for it. So here's how his experiment worked. He had 2 main cabins. One was the infected clothing house, or the fomite house, and the other was the mosquito house. So the infected clothing house had a whole bunch of fomites, people who had died of yellow fever, their clothes really, but it was screened off to prevent mosquitoes. And then in the mosquito house, they had 2 sides, one screened off and one screen with those who had been bitten. And of course, those who were supposed to get yellow fever, the ones in the mosquito house did, and the ones in the infected clothing house did not. And thankfully, none of the infected volunteers died. And then Reed gave all the credit to a local Cuban epidemiologist, which is also unusual. I don't think all credit these days would be given to anyone else. Obviously, we know about Walter Reed Hospital. It's in D.C. It's actually part of the Department of Defense. It's not part of the VA, interestingly enough. And without Walter Reed, we wouldn't really have medical consent forms. He used one of the very first examples of medical consent for these men who were willingly signing up to be infected. And then also the Panama Canal. That's a whole story in and of itself with Walter Reed. It was constructed from 1881 to 1904 by the French, although it had to stop because there were 200 people per month dying, yellow fever and malaria. And actually, the U.S., we purchased this project from France in 1904. France didn't want to have anything to do with it anymore. So then in steps Colonel William Gorgas, and we all know of the Gorgas Institute in Panama. He was well aware of Walter Reed's discovery, and he undertook an extensive sanitation project. It took him 2 years, 1904 to 1906, in which he cleaned up the entire work zone. He improved the water systems, fumigation, larvicide, netting, eliminated stagnant water, and in 2 years' time, he had pretty much virtually eliminated yellow fever and malaria from the canal zone. And finally, the last one I will talk about today, I believe he's the last one, Paul Ehrlich. Paul Ehrlich was a German physician, 1854 to 1915. Paul Ehrlich was an experimenter in dyes and stains, and he stained all types of tissues, living tissue, dead tissue, blood tissue. He actually discovered mast cells and nucleated red cells and distinguished lymphocytes. He was also the first person to coin the term antibody, and he hypothesized the side chain interaction between antibody and antigen and a lock and key mechanism. So he had an interesting thought. He said, well, I'm using dyes to stain tissues, and now I'm using dyes to stain microbes. What if the dyes could not just stain the organisms but kill them? So he tried changing the chemical structures of his dyes, but wasn't able to make much progress. And he had this very famous theory, this magic bullet. You may have heard of Paul Ehrlich's magic bullet. He said, we must learn to shoot microbes with magic bullets. And he was on a quest to find that magic bullet. And he actually began to use a compound called, it was like atoxol, I think, at the time. It was basically arsenic acid. It was an arsenic compound. And he started with this lead compound and began changing its chemical structures in the same way he was changing the structures of his dyes. And he found that his preparation number 606, it could kill trypanosomiasis without killing mice. And he had actually heard at the time, though there may be a relationship between trypanosomes and syphilis, which was just, I don't know where he heard that, but anyway, So in 1909, he cured a rabbit of syphilis with this compound. And right after that, in 1910, they started using this compound. He dubbed it salvarsan. It's called arsphenamine. It's the very first modern chemotherapeutic agent. And he began to mass produce it to treat syphilis. Problem was, it was pretty toxic. It was an unstable compound. It caused a lot of nausea, vomiting, caused liver failure, caused death, but it also cured a lot of people too. And until penicillin was widely used in the 1940s to kill syphilis, the arsphenamine and the updated compound neosalvarsan were used to kill syphilis. Here's a picture of him in his office. I don't know if my office will ever look like that. It's pretty crazy. So Ehrlich won the Nobel Prize. It was the one, I didn't write down the, Paul Ehrlich won, I can't remember which number it was. I think it was probably 1908. So both he and Ilya Mechnikov shared the Nobel Prize that year. And it was really in their recognition of work on immunity, because Paul Ehrlich had discovered the humoral immunity with the antibodies, and then Mechnikov had discovered phagocytes and cell-based immunity. And really, without Ehrlich, we wouldn't have how we research chemical compounds today, how we come up with new drugs. Many times we use a lead compound, and change its chemical structures and find the effect. And that was the very first chemotherapeutic agent, a term that he coined. So I'll leave you with this one quote from Louis Pasteur. He said, "Do not let yourselves be tainted by a deprecating and barren skepticism. Do not let yourselves be discouraged by the sadness of certain hours which pass over nations. Live in the serene peace of laboratories and libraries. Say to yourselves first, what have I done for my instruction? And as you gradually advance, what have I done for my country, until the time comes when you may have the immense happiness of thinking that you have contributed in some way to the progress and good of humanity."